My name is Arnau Dolz. I'm a PhD student at I2CAT Foundation, and it's been supervised by the Universitat Politècnica de Catalunya. And today I'm here to present our project at the NanoSat Lab called Democratizing Space Access, the IEEE GRSS OpenPocketQube Kit, and the PoCat-Lektron mission that has been selected for the Flyer satellite programming. Go ahead. Today we will see about a bit of the project itself, and I will present also the team. On top of that, also we'll see the mission, the objectives, and the motivation of it. Then we will see the platform that we have been developing. However, it will be presented by my colleague Edgar tomorrow, the detailed specifications of the platform. But I will focus on the RFI monitoring payloads. And then we'll see the experiments that we will plan to do, which will consist on the RFI mitigation and the federated satellite system experiment. And then we will conclude this presentation with a bit summary of what have been explained. So, first of all, this project started as a mandatory subject at the Telecom School of Barcelona. And well, what we did is a course called Advanced Engineering Project, and it started in 2021. I was the first generation of students that was participating in this project, and on my master thesis, I came back to put my contribution on it. At the UPC NanoSat Lab, we have several facilities, as we have gone through several missions as well. We have a clean room with ISO 8 certification. We have a thermal vacuum chamber, the vibration table, and Helmholtz coils. In addition, we have a ground segment at Monsec that can be seen here that has S-band antennas and very high frequency and UHF antenna as well. Also, we have an anechoic chamber to test our antennas, as we are part of the telecommunications school. The laboratory is specialized in remote sensing, as it's a part of the Theory and Communication Signal department of the Polytechnical University of Catalonia. And we have endorsing professors that have been participating in so many missions of remote sensing. So they have put valuable experience on our projects. The projects that have been go through the years, it's CubeCat 1, 2, 4, that has been was selected and launched by Flyer satellite this July. CubeCat 5, which was FSCAT, that were two 6U that performed optical intersatellite link and federated satellite systems. CubeCat 6, that was a payload sponsored as second IEEE Grand Challenge and was launched this 2024. And now I will present the PoCat, what corresponds to the PocketQubes that has been selected on the Flyer satellite, and also will be inside the CubeCat 8, that is the CubeSat mission that is being now carried on the laboratory. The project itself began as a subject, as I already mentioned, but then we got funding from IEEE, especially on the Directorate of Education and the FARS Technical Committee. We were funded as part of the telecommunications school to carry on with the subject and to develop the OpenPocketQube Kit, so we could buy all the materials to build them. Here you can see the three PocketQubes, PoCat 1, 2, and 3. The first one, it contains a VGA payload. All of them has the same stack, but what they change is the payload itself. The first one is devoted to educational purposes, so students can play and learn how to integrate a payload. And the other two are the ones that have been selected for the Flyer satellite, and are there to do RFI monitoring and contains two payloads, the K-band and the L-band antenna. With all this, we have already done some training sessions that ended up with the educational purposes of this project. That was why we received the funding. The first one was the training sessions to the MENA region that was carried out this last year. And it will be used, the PocketQube Kit, as in here for the Building Tomorrow's Space Pioneers Design PocketQube Satellite, as the part of Barcelona International Youth Science Challenge. And in addition of that, I will allow you to be able to access the QR for this small sat course that is available on the internet, and it's open source as well. About the team, we are students. We have students from telecommunications engineering, but also from aerospace, and also physics students. It's quite an heterogeneous team, but we can work pretty well. On top of that, we have bachelor students, master students, and me myself, that I'm a PhD student right now. we have also, not only from the Polytechnical University, despite the Nanosat lab is in there, but some of the students are from the Universitat de Barcelona, which is our university in our city. So, the mission itself, let's dip a bit on it. We want to demonstrate that complex payloads can be fitted in 1P PocketQubes. This is one of our main purposes, and we want to study the effects of 5G over the frequencies that are used to study the water vapor in the atmosphere. Also, we want to study the effects that can have on satellite navigation in remote sensing applications, such as PNT networks, especially in L1, L2, and L5 bands. And the last of our objectives is to prove that FSS is feasible on PocketQubes, as it has not been demonstrated until now. The motivation is to get a kit for educational purposes and be able to provide a cost-effective solution, as well as a leading-edge technology as it is. Also, I want to demonstrate that passive remote sensing is a solution that can be used over PocketQubes, and as well the federated satellite systems as a novel concept. Now, how we can resume the mission? The mission can be just described as we want to design, develop, and integrate a cost-effective and modular 1P PocketQube platform, allowing the integration of complex subsystems and payloads to do RFI monitoring in remote sensing and reproduce the FS experiment. Now that I have presented you the mission itself, let's go to see the platform that we have. Here is a picture. This is the stack of our satellite. It's a 1P 5x5x5. And what we have is that we have our PCBs that can be seen in red, and then the lateral connectors and the Pico blade breakout connectors as well to separate between them. Also, we have a patch for the battery here, as well as the bottom structure that right now is made of Teflon. Here we can see all the subsystems that we have. This is PoCat-3, which has the K-band antenna. And at the top of later after the payload itself, we have the onboard computer system and the communications that you can see here. This is an STM32, and this is the transceiver. And then we have the APS, the ADCS, a magnetorquer for this axis, and the battery itself. Also, we can see the solar panels next to it, and the structure at the bottom. The payloads, this is what I wanted to present especially. We want to use the K-band PocketQube and the L-band PocketQube to do RFI monitoring. Why? Because in K-band, which is 26.8 GHz, we want to be able to detect atmospheric water vapor. But the thing is that some applications could cause, especially 5G terrestrial networks and short-range radars, can cause interference on it. So with this payload, we want to see if there's any interference on the band. On the other side, we have the L-band that will look for interference and do RFI over these bands of here, especially for the PNT applications. So we want to demonstrate that we want to check and do RFI over the bands of satellite navigation. Some insights is that this payload is controlled by the onboard computer. There's no intelligence on it. On the whole PocketQube, there's only one microcontroller itself. And, it provides temporal and spectrum samples of the spectrum itself. In the other side, the objective is to monitor the RFI by means of remote sensing techniques, in this case passive radiometry, and achieve RFI mitigation and demonstrate the feasibility of complex payloads over the PocketQube platforms. In here, you can see a description of the system itself. All this documentation is available and it's open source as it's part of the project. So if you want to take a closer look, I'll invite you to visit our wiki. But we can see here it's a classical receiver on RF, which we have the LNA, and then we got to get the RSSI, and then we pass to the onboard computer using the ADC. And in here we can see the K-band we have on the receiver, the bottom part of the RF system, and the bottom part of the RF payload. So you can see that here we finally detect at 3 volts and this power, the RSSI. Okay. This is get more interesting, I guess, which is these are the payloads itself that has been used. Those one here has been tested on drone campaigns. I will show you later. But what is really interesting here is that both payloads are almost omnidirectional. This means that if we want to take samples in case of our ADCS system not working, we could also be able to take samples as well. regarding the monitoring, how we are doing. What we do is we get all this band that we want to study, and what we do is we don't convert it. In there, what we can do is, by small bins, we go just sampling to get cover all the band. In here, we can see the specifications of the subsystem, which I think it's important to check that on K band, for the ones that are involved in communications on PocketQubes and use LoRa, I don't know if there's anyone here, but I guess that some of you will use it, that is an ASM band. This is the 868 megahertz, that is the band that is used in Europe. It's over here. So despite couldn't have happened some leakage over there, we have checked that the payload works properly, and we have seen that you could use this payload without any problem on our communication subsystem, so they are fully compatible. So the process of using this payload, what we do? We take RF signal, and then we filter and we amplify it. Once we have this, we don't convert it to be able to work with it. Then we apply our filters, and we take the RSI measurement. Once we have the measurement in power, we have to take the voltage and take to digital conversion to be able to work with it in our domains, or basically so the STM can understand the signal and manage it. So, and then we finally apply our algorithms to see if there's any information that can be used. This slide is a sum up of the payload workflow, as you can see here. The antenna listens to the environment. Then the PCB itself, the component, is the one that is in charge to down convert and measure the power. And then the ADC is the one that digitalizes this power level to allow the algorithms to detect and process the data. And there's one thing, as this is remote sensing, what we aim is to get information to make decisions. So for instance, be able to decide if there's a signal that is being interfered or any kind of this useful information that on remote sensing bands can be applied. However, it is also important to see that there are three main detections, which is the temporal, which is which we detect the pulses through the envelope, the statical, that can be seen here, which use the third and the fourth moment, and the spectral one that allows us to see it's quite similar to the temporal, but what we do is on the frequency domain. Now, the last part of this presentation is about the experiment that we will perform. In here, you can see the scheme of the federated satellite system that we propose, just to reproduce the FS experiment. And we will also see how it works, the payload itself, to allow us to do RFI monitoring. So, this is the block diagram of the payload. As I mentioned before, the payload itself does not have any intelligence. So what we do is we wait for a signal from the onboard computer to allow us to start working. And once this happens, what we do is to go to all the diagram itself that I will go by it now. But once we finish, we will go to sleep. However, we can also be notified by the onboard computer to stop the measurements as needed. So, what do we do here? On the first step of the block diagram shown before, we check the conditions. So, the conditions is that the satellite must be pointing because we need to take the measurements. Then, a telecommand shall request the measurement to be taken. And then the satellite will take the measurement, must be over the region of interest or using a scheduler can be used to take the measurement over a certain place. We say the geographical area because we also have an Orbital propagator on our system, so we could use it as well. On the other side, we have to initialize the payload. How do we do it? From the onboard computer, we power on the PCBs, and we initialize the ADCS and the digital to analog converter. Then we start the timer, and when this timer starts, we check that the peripherals work properly, we calibrate them, we do some operational testing, and then we start with the timer counting. After that, we go deep into the measurement loop that, as can be seen here, is we do an iteration at each frequency beam. So in the picture on the slide that I showed you before, that we have all the band, what we do is each iteration of this loop that can be seen here is for a frequency beam. So what we do is for each frequency beam, we prepare the variables, we convert the DAC, and we take the bits. Then we process and store the data. And this loop is for each beam. Then what we have is to start the operation, we store the data and go and pass it through the subsystem. And to stop the measurement, we will have to stop all the periphericals and power off the payload. This can be done by the stop timer, or as I mentioned before, by a signal on the onboard computer, as we are using free RTOs. These are the first results that we got on the payloads itself. They have been flown on a drone campaign, and we plan now to put them on the Flyer satellite mission as well. So we wanted to demonstrate that it is feasible. In addition, these payloads are also, well, not the same ones, but we are trying to adapt them to the IEEE Grand Challenge that we have also participated and been selected successfully. And well, this allowed us to test only the payloads and reproduce these experiments that, as we can see here, this is the samples processed. And in here we can see the heat map. This is the drone that takes the measurements. This is the region that we studied that can be seen here. And what we did was to set some radars that were sending random data, as you can see here, that actually were just the points of power. And you can see the heat map here corresponding to this heat map over there. So, now that I presented the RFI mitigation payloads, I will go to the other part of this mission, which is the FS experiment. Well, first of all, I will introduce you the federated satellite system concept. It was introduced by Professor Golkar, and well, it's important to mention that it's a set of spacecraft that engages in opportunistic collaboration with each other during the lifetime mission. So basically, they are not aimed to collaborate directly, but once they have free resources, they will collaborate to each other. We have two protocols, so FEDECOP and OSADP, that basically what they allow us is to do the negotiation phase and the transaction phase. The architectures of federated satellite systems are different, but the ones that we're presenting is distributed, so each node of the satellite of the system shall be able to perform both operations. This allows the PocketQubes to share resources, which is very important to improve their the mission results. So despite their limited capabilities, as they are 1P and they have not that much memory or that bandwidth to transmit, they can start using the federated satellite system to share resources and improve the results of the mission. I will explain just with these slides how to perform how the FS experiments will work. What we do is we are on idle state as there's nothing happening. We have a contact with our ground station that would be at ADCS, and we say, okay, fair enough. We have the contact, so I have a downlink channel. Does anyone want to use it as I don't have to use it? Great. Then the other PocketQube will say, yes, I want to. So once the resource is published, the other satellite must request it. Once it's requested, the resource is blocked, and after the negotiation ends, we create the federation. Once the federation is created, what we do is to consume the resource. In this case, will be the downlink channel. And once the resource is consumed, the federation will end. Also, if there's no intersatellite link available or whatever, the system itself can close the system itself as well. Once this is closed, we go back to idle. And just to conclude, what have seen till now? Well, about the project, it began as a subject at the UPC, and then it evolved to the IEEE GRSS initiative as the OpenPocketQube Kit. We developed 3 PocketQubes, these ones over here, and we have done it in the UPC NanoSat Lab with previous missions experience and also the Helmholtz coils. The academic return will be later explained by my colleague Edgar, but until now more than 70 students have passed through this project, and also more than 10 bachelor theses and 7 master theses have been developed. In addition, more than 3 research papers also have been published only regarding this project. And regarding the mission, well, the top points of here is that we want to do RFI monitoring using the K and L band payloads, and we want to reproduce the F experiment that can be seen here. Finally, the mission itself will be launched as the PocketQubes must be launched together, and we will use a quasi-polar orbit and with a near-zero eccentricity, and we are planning to launch it on Q3 2026 as soon. And well, I would like to acknowledge IS Academy for the sponsorship that allowed me to be here. And here I have the reference to our wiki, and there's another platform with the course of small sets. And here's my contact information. Thank you very much for your attention.
Of course, we're now waiting for questions, but our to be there in the next couple of days. So if you want to chat about creating submission, FSS, then obviously grab them. But yeah, thank you very much. Armin.
Thank you very much. Bye.